The quantum internet is coming. Not tomorrow and not for everyone, but it's starting to work. For the first time, researchers have used ordinary fiber optic cables to send quantum messages across more than 250 kilometers. What could we do with that? Let's have a look. The recent demonstration was for quantum key distribution. As the name suggests, this is the method of sharing secret keys that can be used to encrypt other data. It's a security protocol basically, and an ultra-secure one in that. Because if you use quantum particles, then it isn't possible to intercept the message without destroying it. And if you're fine with destroying it, you'll not get much information out of it either. The demonstration took place in Germany, between Frankfurt and Kehl, with a relay station in Karlsruhe. It basically went by underneath my feet. They managed a quantum bit rate of 100 per second, about as much as the Wi-Fi on the German railway, but enough to share the encryption keys. Quantum keys have been shared before and across longer distances than that, but what makes this experiment notable is that it's been done with almost normal infrastructure. I say almost normal because they didn't exactly use phone cables. Instead, they used a European research network called GEANT that's for research purposes and, among other things, connects computer clusters at high bandwidth. Still, the point is that this is all done with standard commercial fiber optic cables at room temperature and shows that the technology can work outside the laboratory. You may wonder whether this can ever work in a standard telecom fiber with normal non-quantum signals also running through. The answer is yes. We know this because just a few weeks ago, the Japanese company Toshiba announced a different breakthrough. They combined a quantum key distribution with a standard non-quantum data stream in a single fiber, and they demonstrated that this works too. So it seems that while the bitrate for quantum keys is still very low, owing to their susceptibility to noise, we can in principle send them along the already existing fiber optics cables, which, by the way, still have not reached my office. The technology is already attracting commercial interest. The bank ASBC operates a quantum-secure link in the UK that could serve the purpose of protecting large foreign exchange trades, which they have shown to work in a demonstration project. In Switzerland, the telecom company Swisscom trialed quantum keys to secure data between university and supercomputing centers. And South Korea's telecom company is actually offering a subscription service that lets enterprises share quantum keys for a monthly fee. This all sounds very interesting, and doing anything with quantum is currently very timely. But these are all small test projects. In the long run, the question is whether it will be worth the effort and money. What sort of data really needs protection by quantum keys? They're ultra-secure, all right, but for the vast majority of purposes, this security is an overkill. While some of the currently used security protocols on the internet can be cracked with large enough quantum computers, which we don't have and might never have, there are security protocols which cannot be cracked by quantum computers and that do not require quantum keys. They just use more complicated encryption protocols. Indeed, the world is already switching to this so-called post-quantum cryptography. And for most people, that'll be totally sufficient. If I buy a lipstick on Amazon, does the transaction really need to be encoded with a quantum key? Probably not. So it's clearly a niche application that I'm not sure is worth it, even for big financial transactions. What about governmental data or confidential military information? Well, the US National Security Agency has explicitly advised its government against it. They write, NSA does not support the usage of quantum key distribution or quantum cryptography to protect communications in national security systems. Their argument is simple. It's expensive, unnecessary, and very susceptible to noise, which makes denial of service attacks much easier. That said, quantum key distribution is not the only thing that one can do with the quantum internet. It could also be used one day to share quantum information among quantum computers. I have strong doubts that this makes any practical sense. Then again, the same thing could have been said about pneumatic tube travel. And, well, stars evaporate, and this is why the universe will die much sooner than we thought. At least this is what I read in the recent headlines. I guess that's bad news for Brian Johnson, because it'll be very boring for most of eternity, but good news for the rest of us, as we'll not be missing out on much in these last 10 to the 1,000 years. But what are these people even talking about? I've had a look. The headlines are about a new paper that was just published. When they say that stars evaporate, they don't mean that stars boil or something. They mean a quantum process like the evaporation of black holes. This was Stephen Hawking's biggest insight, that black holes radiate and thereby lose mass. This radiation is now called Hawking radiation. In the new paper, they use a comparison to a related effect for the electric force. Suppose you have a big atomic nucleus with some positive charge. That'll create an electric field. The larger the charge of the nucleus, the stronger the electric field around it. Eventually, the electric field will be so strong and carry so much energy that it can create electron-positron pairs. The electron falls into the nucleus, reducing its charge. The positron escapes. This process has never been observed because the nuclei that we can create aren't large enough, but it's probably right. For the electric force, this process reduces the charge of the central body, the nucleus in my example. In analogy for gravity, you'd produce pairs of particles and antiparticles from the gravitational field. These would be pulled apart by tidal forces, and just coincidentally, occasionally, one is attracted to the center body, the other one escapes. This leads to a net loss of mass, so an evaporation. The point of the authors in the new paper is now that this doesn't need a horizon. Yes, they say, if you have a black hole, then the effect is the largest. But strictly speaking, it should happen for any object. The higher the density, the more. A solar mass black hole takes about 10 to the 67 years to evaporate. According to their calculation, a neutron star takes about 4 times as long, white and brown dwarfs even longer. They don't look at other stars because these will all burn out and end up as one of those 4: black holes, neutron stars, and white or brown dwarfs. If what they say is correct, this dramatically changes how the future of our universe is going to play out. Because currently physicists think it looks roughly like this. At the moment, our universe still has nuclear fuel and new stars form. But the new star forming period will run out in 100 trillion years or so. Then the only thing that's left will be highly compact dead stars, brown dwarfs, white dwarfs, neutron stars, and black holes, and dead planets around them. The black holes, which have formed by then, will evaporate. But it takes a long time until gravity collapses and clumps the remaining material. Previous estimates say something of the order of 10 to the 1,000 years or so. But here's the relevant part. If you think that all other compact dead stars also evaporate, this happens much sooner. This is why the authors of the new paper say that the universe will die faster in what they estimate to be merely 10 to the 78 years. So when the headlines say that our universe will decay or die or end much sooner, they don't actually mean the entire universe, but the remnants of stars. Once these are evaporated, there's just thinly distributed particles and darkness. However, please don't swallow this as it is, because that calculation is hugely controversial, and most people I know, including myself, think it's likely wrong. The reason is that this analogy to the electric force just doesn't work. It's true that the evaporation of black holes happens because the vacuum around a black hole decays. This is similar to the example with the charged nucleus. The images you often see are somewhat misleading because the typical size of the particles is larger than the black hole itself. They're really very spread out clouds, but the origin of the radiation is indeed a change in the vacuum. However, for gravity, this only works if the space around the object changes in time. This is the case for a black hole because Hawking looked at the collapse of matter that dynamically forms a horizon. but you don't get an evaporation for a static, unchanging object. The same point was made by John Bears, who writes very clearly, the gravitational field of a static mass does not cause the creation of particle-antiparticle pairs. This is entirely correct. Now, strictly speaking, space around any star will constantly wobble a bit, so yes, you have a time dependence, but it's ridiculously tiny, and that'll hugely reduce the emission of stars compared to black holes. The authors don't seem to take this into account, and this is why I'm quite sure that we'll soon see a bunch of replies to this paper and that the result will almost certainly not hold up. Will this urgent question be settled before the stars burn out? Stay tuned and don't forget to subscribe. Is your red the same as my red? You look at a red apple, I look at a red apple. We both wonder why we're looking at red apples, but we probably agree that the apple is red. Then again, how do we know our experiences are actually the same? For a long time, the answer was, we don't know and we won't ever know. Philosophers called it qualia, and it was supposedly something that science can't test. But scientists just went and tested it. The idea that qualia are unmeasurable comes largely from the work of philosophers like Thomas Nagel and David Chalmers. In his famous essay, What is it like to be a bat? Nagel argued that there is something fundamentally inaccessible about another creature's subjective experience. Even if you knew everything about how a bat's brain works, you still wouldn't know what it's like to be a bat. That, according to Nagel, is the essence of qualia, the private subjective side of experience that can't be fully captured by physical descriptions. David Chalmers later expanded this idea with what he called the hard problem of consciousness, which is the idea that even if you understand all the physical processes in the brain, you still haven't explained why experience feels the way it does. This philosophical view made qualia seem almost mystical, cut off from scientific investigation. I've always thought this is bullshit. You can measure what's going on in the brain, therefore you can study what experience means in scientific terms. You cannot, of course, yourself experience the same as some other person or bat or carrot because you don't have the same brain. But give it some time and we can find the next closest approximation to someone else's experience that works on your circuits. And in a fascinating new study that just came out a few weeks ago, scientists say that it might actually be possible to measure qualia, or at least compare them, in a meaningful way. The authors of the new paper recruited 35 participants and showed them different colors while measuring their brain activity using fMRI. Their goal was to find out if the experience of specific colors, like red or blue, creates consistent patterns in the brain. They compared the brain signals across participants and indeed found similarities that matched the perception of the same colors. This is the first time scientists have objectively measured qualia, subjective experiences, by identifying neural signatures that are the same for different people seeing the same color. In other words, they demonstrated that your red is, at least structurally and approximately, likely indeed the same as my red. This experiment is part of a broader shift in how we think about consciousness and qualia. It's a move away from philosophy to something that can be scientifically measured, quantified, and understood. For example, in another recent study, the neuroscientist Anil Seth and co-authors have proposed a mathematical framework for consciousness in general and qualia in particular. They propose that subjective experience comes from our brains trying to constantly make predictions about what it expects to perceive based on past experiences. Then it compares these predictions to the actual sensory input. When there's a difference, the brain updates its model to better match reality. In this description, qualia are the key elements of this predictive algorithm, those experiences that are particularly versatile at describing sensory input, like color, for example, or the orientation of your body standing upright or hanging upside down from a cave. Seth and his colleagues argue that if we understand how this prediction and correction process works, we might be able to map subjective experiences, or qualia, in the same way the recent study mapped color experiences. And it's not just academic curiosity. There's even an institute dedicated to this very question. It's called the Qualia Research Institute, and their goal is to create a precise mathematical framework for understanding subjective experience. They want to map the state space of consciousness, that is, they want to understand the landscape of experience. Even philosophers are coming around to the idea that maybe, just maybe, subjective experiences aren't as philosophical as they once thought. In fact, there's a new book called The Metaphysics of Color from two philosophers that make a surprising argument. Colors are real.
We argue that there is no good reason to think that colors are less objective than, say, temperature.
What does all of this mean? If these researchers are right, then we might be on the edge of a new way to understand how experience happens and eventually also how to create it. Because imagine how amazing it'd be if you could share experiences with other people, or bats. I mean, who wouldn't want to know how it feels to breed a new human pandemic? It's not every day that I have a new theory for dark energy and dark matter to talk about. But yes, today I can report that a physicist has found a way to solve both problems at the same time. 2 for the price of 1. Somewhere a grad committee is very happy. In our current theories, space and time are fundamental. It's a smooth continuum that isn't made of anything else. But if the history of science has taught us one thing, it's that more often than not, things are not what they seem to be. So maybe space and time are just made of something else. And then what, you may say? Well, even if we don't know exactly what they're made of, that gives us a general expectation. It's that the continuum of space and time should be imperfect. They should have irregularities. They should have defects, much like a crystal. The interesting thing about defects in solids is that even if they're rare and tiny, they do change some observable properties of the entire crystal. Like, for example, impurities of nitrogen or titanium change the color of diamonds to red or blue, creating rubies and sapphires. But if that was true, that space-time has defects, what would they look like? Again, we don't know, but we have a general expectation. For one thing, a defect in space and time must be localized in space and time. So that makes them very different from defects in a crystal, which are only localized in space, but not in time. A localization in time means basically that the defect is only present at one specific moment. And the other general expectation is that the defect can't be described by a smooth space-time, because, well, otherwise it wouldn't be a defect. Of course, that brings up the question of how do you use a theory with a smooth space-time to describe something that, per assumption, doesn't fit into the theory? You do it with singularities, points where the theory breaks down. So a space-time defect is a singularity. It doesn't itself carry energy or mass, but as a singular point, it can break with the usual conservation laws, and that'll make it appear as if it has a mass or energy. It's like new books keep appearing on my desk, even though I swear I didn't order them. Maybe that's what dark energy is made of. By the way, this video comes with a quiz that lets you check how much you remember. But back to the singularities. We do have singularities in Einstein's theory inside of black holes hidden behind a horizon. And, at least mathematically, we can have naked singularities that don't have a horizon around them. But the space-time defects are very different from those because they only appear at one instant in time. We talked talked about a similar idea a few months ago when I reported on a paper according to which dark matter might be caused by singular shells surrounding galactic cores. The same author is now back and says that this idea can also give rise to dark energy. In a new paper, he shows that with a suitable distribution of these singular defects, you get dark energy. This suggests that both dark energy and dark matter might really be phenomena caused by the imperfections of space and time, and that there is a deeper fundamental level underlying space-time. I have to make a confession here, which is that I wrote a few papers on defects in space-time, and I have two misgivings about this idea. The first is that what you get out of the author's theory is what you put in. You just have to choose the distribution for the defect so that they give you dark energy and dark matter, et voila. My second misgiving is that the author doesn't cite my papers. Clearly the biggest flaw in his theory. Okay, but that's no reason to dismiss the idea. You might say, well, if you have to assume that these defects just happen to look like dark matter and dark energy, then why not stick with dark matter and dark energy? The reason is that if these dark phenomena really come from space-time defects, the observable consequences might be slightly different. Most importantly, they'd have an effect on light, because light feels space and time and its distortions, whereas dark matter and dark energy are typically assumed to not do anything to light. This is indeed much like defects in a crystal affect the scattering of light, causing colors. In space-time, it's somewhat more complicated, and if I'm going by the results of my own work, the effect is stronger at smaller energies, loosely speaking, because smaller energies mean larger wavelength, which sweeps over more defects. So I'm super biased, of course, but I like the idea in principle. The maths is very rudimentary at the moment and frankly unsatisfactory, but it's a new approach that might lead us into a fruitful direction. I also find the idea oddly comforting. If the universe is full of imperfections, that gives all of us an excuse. Thanks for watching. See you tomorrow.